Good afternoon, everyone. Thank you all for being here today. My name is Pavlo Trishin, and I'm pleased to welcome you to this conference. Let's begin. Let's begin with the first section of the day. It's digital and intelligent manufacturing engineering. Now I'd like to invite Dmitro Lysyak, Hitoshi Soyama, Bogdan Modrik, Christian Raya, and Adriat Charit to present on the topic of surface and corrosion properties of CC 304 alloy preceded by ultrasonic impact beam, some submerged laser beam, cavitation, and wet shot beams. Let me show my screen. Let's start.
Ты можешь найти то, если ты мне доверяешь?
Так, зараз. 1 minute, please.
Today I would like to present a dear participants. Steel 304 processed by ultrasonic impact pinning, submerged laser pinning, cavitation, and wet shot pinning. This work was implemented in collaboration with the Tohoku University Institute for Metal Physics of the National Academy. Dear participants, today I would like to present a study about surface and corrosion properties of stainless steel 304 processed by ultrasonic impact pinning, submerged laser pinning, cavitation, and wet shot pinning. This work was implemented in collaboration with the Tohoku University, University of Idaho, and Kurdimul Institute for Metal Physics of the National Academy of Science of Ukraine. My name is Dmitro Lesik, and I am Associate Professor at the Laser Systems and Advanced Technologies Department of the National Technical University of Ukraine, Igor Sikorsky Kyiv Polytechnic Institute. Also, a postdoc fellow at the Aeronautics Advanced Manufacturing Center of the University of the Basque Country. Improving the surface integrity and corrosion resistance of stainless steels by changing the structure and surface microrelief has remained relevant because the destruction of stainless steel products initiates from the surface. Recently, to enhance the surface properties of stainless steels, much attention has been paid to advanced surface finishing technologies, such as severe plastic deformation processes, using a laser shock peening, water jet cavitation peening, ultrasonic nanocrystal surface modification, water jet shot peening, and ultrasonic shot peening. In particular, the schematic description of the surface treatment process for ultrasonic impact treatment, laser shock peening, and water jet cavitation peening is presented on this slide. The aim of this work was to determine and compare the effects of the modified surface morphology and structure in the near surface layer on the corrosion behavior of completely modified on the surface after the ultrasonic and shot peening, while the laser and cavitation treatments led to mirror change in the surface relief due to the rather roughness of the original specimens. This is attributed to the plastic deformation by laser shots and cavitation bubbles, which occurred mainly with micro irregularities of peaks, as compared to that of the laser cavitation and wet shot peening. The surface microrelief of the ultrasonic treated sample is remarkably smoother. Here you can see after ultrasonic, the roughness was the best as compared to the other peening techniques. And this is due to, because ultrasonic during the ultrasonic treatment, forming the ultrasonic tract 15 millimeter ultrasonic tool and rotation speed of impact had with 7 pins. Considering the near surface micro-hardness, it's observed that the Vickers values were increased after all peening methods used due to the near surface nanostructuring, as well as increase in dislocation density and Martensite transformation in the surface layer. The hardening depth was respectively achieved about 150 micrometers, 225 micrometers, 400 micrometers, and 800 micrometers after the ultrasonic wet shot cavitation and laser peening techniques used. As shown, the size of martensitic grains in the outmost surface layer range in a nanoscale regime due to the severe plastic deformation occurred, and it's slightly larger for the ultrasonic and wet shot process than those formed after the cavitation and laser peening techniques. The residual macro stresses was recorded, the compressive residual stresses were recorded regardless of the processing method. Here you can see the green line. It's characterized by residual stresses. The significant improvement in corrosion resistance and impact treatment induced oxidation of metal components obtained by the ultrasonic impact treatment methods, and it's in good agreement with previous works. The severe plastic deformation of the near surface layers by the multi-pin ultrasonic process resulted in more strain-induced martensite and flatter surface texture with low roughness than the cavitation, laser, and wet shot deformed samples. Also, all the studied samples are characterized by some passivation region. However, the most indicative passivation region with almost constant passivation current was observed after cavitation treatment. The result indicates that the ultrasonic processing improves corrosion resistance more significantly by forming more favorable surface microrelief. The highest passivation ability was also found after cavitation and ultrasonic treatments due to single nanoscales austenite formed in the top surface layer. Considering the surface microhardness, hardening depth, residual macro stresses, nanostructuring effect, and structural roughness parameters obtained, the laser cavitation and wet shot pinning treatments can be recommended for surface finishing of complexly shaped or small size austenitic stylus steel part, while the multi-pin ultrasonic treatment would be applicable for surface finishing of the large size components with simple geometry. The author gratefully acknowledged to several projects, including the European Union's Horizon 2020 Research and Innovation Program for supporting this work. Thank you very much for your attention.
That was a very interesting and informative talk. Are there any questions from the audience? Okay, I have a question. Okay, my question. Which of the considered methods of mechanical surface hardening has greatest effect on the structure of the top layer of the CS 304 alloy? Дмитро Лисак, are you here? Let's move on. Sorry.
Now I know. Yeah. Yeah, can you hear me? Hello, everyone.
Yes, we hear.
So could you repeat the question? I remember, yeah, what was the best method in context to obtain, I think, the structure, yeah, you said. Okay. No, first of all, we would like to set the studied methods, what we considered in this work, resulted information of the nanoscale grain structure. Nevertheless, taking account the near surface microhardness and martensite formation tendency obtained, in particular, the wet shot pinion and ultrasonic impact pinion induced higher volume fraction of the martensite in this studied steel. And in particular, the ultrasonic treated samples was characterized by higher volume fraction of martensite, I think reaching about 50%, which can be another explanation for the observed hardest top layer. That's all.
Thank you, Дмитро. Я трохи тут плутаюсь з мікрофонами. Sorry. Now I'd like to invite Володимир Смоквіна, Галина Ініцька, Мона Оленник, Григорій Петащук, Валерій Лавріненко to present on the topic of improving the physical, mechanical, and physical chemical characteristics of synthetic diamonds to increase the efficiency of diamond grading tools.
Да попробуй еще раз.
Hello everyone, let me introduce our work. The performance of any diamond tool is largely determined by the properties of diamond. The aim of the work was to find new approaches to increasing the efficiency of using diamond grains by flotation separation. The literature provides examples that it is possible to artificially change the functional characteristics by increasing the degree of diamond defects under the influence of such deforming factor as mechanical or thermomechanical treatment. However, in our case such characteristics can be achieved by flotation separation. This review of publication has shown that the thematic orientation of known publication of the field of diamond powders focuses mainly on two applied aspects of flotation. The first of them concern the enrichment of the diamond synthesis product, and second, a method of improving the quality of already manufactured conditioned synthetic diamond powders in terms of their individual characteristics, in particular the static strength of the grains. Therefore, the scientific and practical interests of their work is the research of development of methods for directed change, namely improvement of the functional characteristics of synthetic diamond grinding powders for abrasive purposes using flotation separation. The scheme of the research is given on the slide. The research was conducted for diamond grinding powders of this synthesized in the nickel, magnesium, and carbon system, and products of its flotation separation foam and chamber. The research methodology included determinant of influence of various methods of pretreatment of diamond grinding powder grains during flotation separation on the change of their physical mechanical and physical chemical characteristics. Chemical liquid phase treatment was used. After separation, the technological characteristics of the separation were determined, in particular the percentage degree of separation. Separation. The physical and mechanical characteristics of diamond grinding were determined: static compressive strength, total content of impurities and inclusions, grain compositions assessment index, it's large, main and small fractions, specific electrical resistance, specific magnetic susceptibility, etc. The results of flotation separation of the initial diamond grinding powder and the characteristics of the properties of the initial powder and the products of its flotation distribution are given in this table. It was established that under the influence of flotation separation of diamond powder, which occurs in a gravitation field, it is possible to obtain powders whose physical and mechanical characteristics significantly differ from the characteristics of the original powder. In particular, in the process of research diamond powder foam product, which an increased strength index under static compression by 23.8%, increased uniformity of strength by 25%, and a significantly reduced proportion of impurities and inclusions was obtained. During flotation separation, the morphometric characteristics change in terms of grain shape and grain composition. On this slide, you can see photographs with morphometrics characteristics of grains of during powders of diamond samples. It's initial powder, foam flotation product, chamber flotation product. Based on the obtained data, a calculation was made to determine
О боже, там так громко.
homogeneity of the studied
Да.
abrasive powders by morphometric characteristics and by the static strength of the grains using computer analytical method. And you can see numerical information on morphometric characteristics on this table. Thermomechanical treatment and additional sorting of diamonds on R20 sieves allowed to increase the content of the main fraction by 11.4% and increase the uniformity of diamond powders in terms of linear grain size by 80% and 18% and also ensure an increase in the developed surface area by at least 30%, which ensure an increase of abrasive capacity. That is, for foam flotation sorted diamond powders, the main factor in increasing wear resistance is an increase in their strength index, but for chamber flotation sorted diamond powders, and main factor is the proportion of impurities in them. Wear resistance of a diamond will it is foam flotation sorting of diamond grinding powder that is the most effective. Moreover, with increasing grinding productivity, this efficiency increases. In conclusions, we must say that the results of this study show that flotation separation of diamond grains into a foam flotation product and a chamber flotation product occurs, and that this method allows changing the functional characteristics of diamond by improving for its further use in abrasive tools. Knowing in which growth system a diamond is synthesized can help us to control and operate its physico-mechanical and physico-chemical characteristics. Thank you for your attention.
Thank you for your presentation. It will be very interesting. Now, are there any questions for my audience? Okay, I have a question. Volodymyr, are you here? Can you turn on your microphone?
Yes, I can.
Okay. My first question. Your research shows significant improvements in wear resistance than using foam fluctuation products at higher productivity rates. Have you investigated the maximum productivity threshold, whereas benefits might diminish? Diminish. Difficult word for me.
Yeah, thank you for your question. The foam flotation product allows us to isolate diamond grains and that have not only great crystal strength. Due to the low content of intracrystalline impurities, but also a different number of cutting edges. It indicates that we can clearly distribute such grains for different type of tools. For example, for processing stone, rocks, and even for dressing tools. As the productivity, we plan to conduct this in the future study, since this product has shown high performance characteristics.
Okay, thank you. Do you have any questions? Natalia?
I can.
Okay.
The paper mentions that chamber flotation products have larger grains and higher roughness. Could these characteristics be advantageous for specific machining applications where controlled surface roughness is desired despite their lower overall wear resistance?
Thank you for your question. Yes, in the study, we received two types of products, and in the chamber product that we can use in grinding wheels for sharpening or material removal operations, since this diamond, due to their high rawness, have high characteristics until new cutting edges appear on the grain. This process is called self-sharpening of the grinding grain, and allows not only to have continuous cutting ability, but also to reduce the temperature in the processing zone. That is lowest strength and wear resistance has its advantages in specific types of processing, such as grinding glass, ceramics, hard alloys, etc. But they are not bigger or than foam flotation product, than grain in foam flotation product.
Yes.
Thank you. Thank you very much. Now, please welcome Mykola Ryabchikov, who will be speaking about creating wave transmission with a flexible magnetic element and a non-contact magnetic generator.
Greetings to everybody. Topic of our research is creating wave transmissions with a flexible magnetic element and a non-contact magnetic generator. Harmonic wave transmissions are widely used in innovative machines and equipment. Deformation of the flexible element occurs due to the rotation of the wave generator, the shape of which affects the stress in the shell and gear teeth. The use of a non-contact generator based on an adjustable magnetic field can largely solve this problem. This principle can be applied to magnetic flexible materials created on the basis of the introduction of appropriate microcomponents into the structure. Magnetic micropowders based on a mixture of divalent and trivalent iron oxides are created as a result of the synthesis of ferrum SO4 and ferrum chlor 3 components. Solutions of these substances are mixed in a reactor with the addition of NH4OH. As a result of the synthesis, a powder in solution is formed. This powder is a mixture of divalent and trivalent iron oxides. The resulting mixture was applied to the textile material. In the optical microscope, clusters of magnetic microcomponents located in the irregularities and pores of the fibers were observed. Figures shows fibers and particles assembled into clusters. Textile material consisting of fibers with applied microcomponents acquires magnetic properties. Increasing the concentration increases the magnetic characteristics. The experiment to determine the force with which the material is attached to the magnet was carried out on scales with a change in the magnetic flux density from 0.8 to 1.6 millitesla and a distance of up to 25 millimeters. The general principles of creating wave gear consist in the deformation of a flexible cylindrical element with teeth. Its deformation can be ensured by the rotation magnetic field by the rotation of the generator rotor with electromagnetic excitation. The obtained results make it possible to create shells that deform under the action of surface loads from the coils located inside. The magnetic field for a three-phase system can create a rotating magnetic field, then can deform the shell according to a given law. The resulting textile material has magnetic properties. This material is quite flexible and can easily be transformed into various forms. Made in the form of cylindrical shell with a fixed toothed crown, this material turns into a cylindrical flexible element. Epoxy composition was used to fix the shape of the resulting element.
Алло, в 3 часа конкурсная.
Secured a stable cylindrical shape with the possibility of deformation. The specified semi-momentless theory was used to determine the necessary deformations under the action of surface loads. The radial displacement can be found as shown on slide. Profiles of deflections for the wave transmission envelope found by the proposed method are shown too. Thus, field micromagnetic flexible materials create opportunities for deformation under the action of a rotating magnetic field. This fact determines the prospects of creating wave transmissions without the participation of rigid wave generator. At the same time, the geometry of electromagnetic devices can provide the necessary parameters of the magnetic field to create a profile of deformations that correspond to the best conditions for the engagement of the flexible gear ring with the teeth of the fixed body. Thank you for your attention.
Thank you. Thank you very much for your interesting presentation. Are any questions from audience? Okay, my questions. What are the limitations of the proposed system in the term of deformation force or operating frequency?
Yeah, thank you for a question. We just have created a prototype of our transmission, and we are currently conducting some experiments, and we discovered that magnetic induction of millitesla level, and this is limitation of our prototype, is enough to create a force that deforms flexible element in sufficient size.
Thank you. Natalia, do you have question?
Yes, I have. What are the main challenges when integrating a magnetic generator into real wave transmission designs?
Thank you. There are a lot of challenges because this gear and this transmission is rather new. But as we think, the biggest challenge relates to possible fatigue of flexible element.
Okay.
Thank you for your
Thank
answer.
you. Thank for you.
Now, I would like to invite Pavlo Trishin, Alena Kozlova, Natalia Chernavol, and Yuri Vnukov to present on the topic of experimental study of vibration excitation conditions during turning.
Dear colleagues, it is my pleasure to present to you a report on topic, an experimental study on vibration excitation conditions during turning. This study explores the critical factors that lead to vibration phenomena during the turning process. aiming to enhance our understanding to their causes. On the one hand, the problem of vibration excitation during machining is non-trivial, since it covers a large number of cutting types when machining various parts on cutting machines of different designs. On the other hand, the appearance of vibration reduces the quality and accuracy of manufactured parts and the service life of machines and tools. Furthermore, it creates uncomfortable working conditions for operator and significantly reduces the economic efficiency of machining process. Currently, extensive practical experience in technological methods of vibration suppression in production environments has been accumulated. Additionally, analytical methods of predicting the conditions of vibration excitation and ways of its suppressions have been developed and are being improved. Nevertheless, some physical phenomena of vibration excitation remain unclear and are used in the form of hypotheses and assumptions. In the works of founders of the theory of regenerative vibrations, Tlasty, Tobias, Merritt, the limits of vibration stability of machine tools were defined using the limiting width of cut and machine spindle speed. First, asymptotic boundary defines the limiting depth of cut which provide stability at all spindle speeds. Second, tangential boundary represents the stable region in the low spindle speed zone. Third, lobed boundary shows lobes of stability that are particularly effective in a high spindle speed zone. The developers of regenerative vibration theory considered that the main reason for the excitation of vibration is cutting by the vibration trace left on the cutting surface from the previous revolution of the workpiece or passage of the cutting edge of the tool. In their opinion, the conditions of regenerative vibration excitation are the same for all types of cutting, such as drilling, milling, turning, riding. For more than 70 years, the main methods to determine the dynamic stability of machining is the construction of stability lobe diagram, SLD. The basic provision and hypothesis of the regenerative theory are used to construct SLD. Continuing to develop its analytical parts for various modern cutting conditions. At the same time, the stability boundary of machine tool operation is determined in the wide range of spindle speeds. A typical SLD, which is usually divided into low spindle speed machine zone up to 3000 to 4000 RPM and high spindle speed machine zone. Most machine tools operate in the zone of low spindle speeds, including lathes. The key factor in the mechanism of excitation of regenerative self-oscillation underlying the construction of SLD is the fast shift of waves of the cutting surface of adjacent revolution of the workpiece. The theory proposes a direct relationship between the remainder of the wall wave on the length of one part revolution and the fast shift of adjacent waves. However, the simplification adopted in this methodology, such as the similarity of the dynamics of cutting types and the consideration of machine vibration only the frequency domain, causes a number of contradictions according to the metal cutting theory. For the turning process, the characteristic of motion are cutting speed and feet per revolution from the point of view of chip formation process. Therefore, then studying vibration, it is important to consider the cutting speed rather than making the spindle speed the determining factor. The main goal of this study is to determine the key characteristic that defines the vibration intensity during turning. Longitudinal and phase turning under orthogonal free cutting conditions of rigid parts were used for experimental studies. The test parts were made of structural and tool steel and had three different shapes: cylindrical, tubular with a wall thickness equal to the cutting width, and disc-shaped. The turning process was performed on CNC lathes using coolant. The variation of process parameters was within the following ranges: cutting speed from 100 to 350 meters per minute, feet per revolution from 0.1 to 0.3 millimeters per revolution, and cutting depth from 0.5 to 2 millimeters. Different designs, cutters, oscillator with single degree of freedom with rectoral holder cross-section were used for the experiments, allowing to study the vibration excited under different cutting conditions. First, a cutter oscillator with single degree of freedom along the x-axis allowed the investigate the regenerative vibration during cutting without the influence of coordinate coupling, then cutting only along the vibration trace. Second, a cutter oscillator with single degree of freedom along the z-axis allowed to study the vibration without regenerative effect and the influence of coordinate coupling, then cutting only the vibration-free trace. The displacement of cutter oscillator from the position of initial equilibrium was measured by inductive sensor, the signal from which was recorded on a personal computer in the form of oscillograms. On the quiet of oscillograms, the following parameters were measured. Initial equilibrium position of the cutting edge before plunge cutting begins. Static equilibrium position of the cutting edge at any time during cutting. The number of revolutions of the workpiece in the initial plunge cutting section at which the nominal cutting thickness is set. Static deflection of the cutting edge. Cutting edge oscillation amplitude. Frequency of oscillator oscillation during cutting. Frequency of oscillator oscillation at idling. Natural frequency of cutter oscillator oscillation. Fast shift of the waves on the cutting surface. Damping coefficient during cutting and idling. The experimental results of the test conducted with single degree of freedom cutter oscillator confirmed two physically different mechanisms of self-oscillation excitation than were first described in the work of Tobias. Then turning with cutter oscillator with single degree of freedom along the x-axis, regenerative self-oscillation are excited as a result of the real cutting thickness variation. However, during cutting with a cutter oscillator with a single degree of freedom along the z-axis, self-oscillation are excited as a result of the instantaneous cutting speed variation. Experiments to determine the effect of spindle speeds on the intensity of regenerative self-oscillation during longitudinal turning of its cylindrical parts were conducted at constant cutting speed 150 meters per minute, at which intense vibration are excited, using a cutter oscillator with single degree of freedom along the x-axis. The constant cutting speed was assured by using different spindle speed from 362 rpm to 1080-36 rpm and different workpiece diameter from 26 mm to 132 mm. It was experimentally identified that despite different parameters of the cutter oscillator than using a cutting edge with a wear area, HF is greater 0.05 mm, the zone of maximum vibration corresponded to a certain value of the critical cutting speed. Moreover, increasing or decreasing the cutting speed from the critical value led to reduction in the vibration amplitude. Changing the cutting parameters, depth, feet, rake angle, resulted in change of self-oscillation amplitude, but did not lead to the change the critical cutting speed value. These dependence were first observed by Kuchma. Increasing the cutting width, increasing the self-oscillation amplitude, while increasing the cutting thickness and positive rake angle decreased it. The flank wear length of the cutting edge had an exceptionally significant effect on vibration suppression. With the increase in flank wear length, the amplitude of self-oscillation reduced. The cutter oscillator with single degree of freedom along the z-axis does not structurally support regenerative self-oscillation, but the same dependence between cutting condition and self-oscillation amplitude were observed for longitudinal turning of a tube as for the cutter oscillator with single degree of freedom along the x-axis, then turning a cylindrical part. Another way to experimentally test the effect of spindle speed on the excitation of a regenerative self-oscillation was turning a disc with hole diameter 32 mm and outer diameter 130 mm with a cutter oscillator with single degree of freedom along the x-axis. The disc turning was performed with constant spindle speed from 300 rpm to 700 rpm from the center to the periphery of the disc. Due to the increase in cutting diameter at each moment of time, cutting speed increased correspondingly. Then the minimum cutting speed, the min, was reached. Regenerative self-oscillation started to excite, leaving a vibration trace on the machined surface of the disc starting from the diameter d min. As the disc turning continued, the vibration trace disappeared at diameter d max, at cutting speed v max. Thus, a vibration ring remained on the machining surface between the diameter d min and d max. The average diameter dA of this ring determined the critical cutting speed, at which the amplitude of vibration was maximized. The following discrepancies between the experimental results and theory of regenerative self-oscillation for low values of spindle speed were established. First, the location and boundaries of the regenerative self-oscillation excitation zone was determined by the value of the critical cutting speed. At the cutting speeds above or below the regenerative self-oscillation zone, vibration-free cutting were observed. Second, the remainder of the wall wave on the cutting surface was not related on the magnitude, on the phase shift of adjacent waves on the cutting surface. And the remainder of the wall number of waves on the cutting surface does not have influence on the magnitude of the phase shift of adjacent waves on the cutting surface. Two series of experiments were conducted to investigate the impact of spindle speed on the excitation of regenerative self-oscillation. The results of experiments show that the cutting speed is the main factor which determine the amplitude of vibrations. Thus, it should be used instead of spindle speed during study of the cutting process's dynamics.
Thank you, authors, for your presentation. There are any questions from the audience? Natalia, do you have questions?
I have questions. The first question. Your research found discrepancy between experimental results and regenerative self-oscillation theory at low spindle speeds. Could you elaborate on why cutting speed rather than spindle speed appears to be the main factor determining vibration intensity?
Thank you for your question. The results of the experiments showed that then changing the spindle speed in the wide range, the vibration amplitude did not change. At the same time, when changing the cutting speed from 50 to 300 meters per minute, we observed a range of speeds in which vibrations were excited, and speeds above or below which there were no vibration at all. Moreover, the maximum vibration amplitude corresponded to the specific speed value, and above or below this value, the vibration amplitude disappeared. Please, next question.
Okay. In your conclusions, you question the application of stability lobe diagram, SLD, for predicting turning process stability. What alternative approach would you suggest for better prediction of vibration stability during turning?
Thank you. In our work, we do not propose alternative methods for predicting oscillations during turning. We experimentally show that the use of stability lobe diagram, SLD, during turning is not correct.
Okay, thank you.
Now I would like to invite Володимир Гурій, Ігор Гурій, Тетяна Гурій, Мар'яна Бартазюк, and Rostislav Gera to present on the topic of modeling of the amplitude response of the process of thermodeformation treatment of flat surface of machine parts.
Hello, my name is Volodymyr Gurey. I am from Lviv Polytechnic National University. I would like to present our scientific work. The topic is modeling of the amplitude response of the process of thermodeformation treatment of flat surfaces of machine parts. The performance properties of machine parts are noticeably affected by the quality parameters of contacting surfaces and their surface layer, which are determined by the geometric, stereometric, and physical and mechanical characteristics and the relative location of micro-roughness on the coating surfaces. The parameters presented above are significantly affected by various technological methods of surface treatment. Surface treatment methods that hide changes in the quality parameters of the surface layer of parts can be divided into two groups: the application of various types of coating and their modification. 15 years ago began to develop the new direction which called surface engineering, with the development of which began to develop the direction of formation material with nanostructures and nanomaterial. Stressed metal surface layers with a nanocrystalline structure can be formed during modification. The grain size of a nanocrystalline structure is below 100 nanometers in at least one direction. Nanomaterials or materials with nanocrystalline structure have absolutely different properties from large crystalline materials, and they also have an anomaly of physical properties. For example, as the hardness increases, the viscosity increases too. The stressed layers grain structure on massive parts can be ground by the processing methods using highly concentrated energy sources, intensive plastic deformation, and a combination of these methods. Also, to improve the performance properties of machine parts, it is necessary to use technological methods of surface treatment, during which stressed surface layer with a nanocrystalline structure are formed on the treated surface of machine parts. Such methods are technological methods of processing using highly concentrated energy sources. These include laser, plasma, electron beam. Surface plastic deformation methods are used as a surface strengthening methods, and also another method is to apply the coating. Coating good method, but differ from the previous two in that the protective coating has a clear boundary between the main material. When using these methods of surface strengthening, the metal surface layer of machine parts surface is modified, and our thermodeformation treatment is treatment that combines two types of the stressing: highly concentrated energy sources and intensive plastic deformation. The thermodeformation treatment is similar to grinding in terms of process kinematics and execution. It is carried out using surface grinding machine tools. A special metal tool disc with a diameter equal to the diameter of the abrasive wheel is mounted instead of the standard abrasive wheel that used in the grinding machine tools. A linear velocity of 60-90 meters per second is required at the periphery of the contact area of the tool with the part to generate a concentrated heat flux. The grinding wheel velocity on the machine tool is 36 meters per second. So, to increase the tool velocity, it is necessary to upgrade the grinding wheel main drive unit. The contact area of the tool with the part workpiece is subject to intensive friction of the tool on the treated surface during the thermodeformational treatment, and intense thermal energy sources is generated in the contact area as well as a shear deformation of the surface layer. Transverse grooves were formed on the work surface of the disc to increase the thickness of the stressed layer and to guide its structure. The transverse grooves created an additional source of impact load in the disc workpiece contact area. The tool's work surface is discontinuous. In other words, it is a smooth work surface with a groove alternate. The surface layers change the structure, physical, mechanical, and electromechanical characteristics of the metal, increase their hardness, decrease the grain size, change the chemical and phase composition of the metal, the magnitude and sign of residual stresses, which significantly affect the performance of machine parts during operation. A highly concentrated energy flow is formed in the area of a contact of the tool with the treated surface during the high-speed friction at the friction treatment process. Stressed layers with a non-crystalline structure, white layers are formed in the surface layer of the machine parts. White layers have increased hardness and viscosity, dislocation density, and residual austenite, crashed grain, residual compressive stress are formed compared to the base metal. This work continues the work described in the article published in the Journal of Manufacturing and Materials Processing. It shows that with the increase in the amplitude and frequency of impact loads, the contact zone between the tool and the workpiece increases the thickness of the stressed layer. I would like also to add that our method refers to finish method of manufacturing the working surfaces of machine parts. However, in practice, during finishing operations, efforts are made to minimize dynamic processes in the contact zone between the tool and the machining surface. Therefore, this study aims to investigate the stability of machining using a tool with a different numbers of grooves on its working surface. To investigate the dynamic processes that occur in the course of the thermodeformation treatment, we developed a scheme of the machine tool elastic system. To do this, we divided the machine into several nodes, each of which represents a separate masses. The following scheme is a three-mass model. The machine bed is assumed to be a part with a conditionally infinite mass, to which all other masses are tied. The relationship between the individual masses is described by elastic and damping links. The impact among the workpiece and periphery of the disc is given by using a contact stiffness, C7, and energy damping, μ7, of the local elastic plastic deformation of the part's surface. The above scheme is replaced by an equivalent calculation scheme of the machine tool. Here is presented the system of differential equations that describe the elastic system of machine tool during the thermodeformation treatment of the machine parts. Flat surface with the tool with transverse grooves of the periphery. The process of thermodeformation treatment is a discontinuous one, meaning that to increase the thickness of the stressed layer, it is necessary not only to increase the heat and temperature, which must be higher than the phase transformation points in the disc workpiece contact area, but also to increase the shear deformation, which is formed by alternative between the disc's smooth part and the groove. The main condition for selecting the groove width was the complete removal of the contact between the tool and the part. Based on the mathematical modeling of thermoelasticity in the disc workpiece contact area, the result of changing stresses were obtained. The disturbance of machine's elastic system is caused by the grooves and on the tool's working surface. First, consider the case when the ratio of the smooth part of the tool to the grooves is equal. We assume that the disturbance of the acceleratory system will occur according to the law F0 multiplies sinus of omega t, where omega is the angular velocity of the tool on which the grooves are located. Therefore, the disturbance of the oscillatory system will be as follows: omega tool multiplied into n equal omega. To study the influence of the grooves number of the disk peripheral on the dynamic characteristic of the thermodeformation treatment, we will analyze the system using amplitude response. Substituting the complex quantities into system, we divided the left and the right sides on the resultant equation by e power of I omega t. We obtain the system. Using the MathCAD software, we perform a symbolic solution of the systems of equations and find the modulus of the complex amplitudes. Due to the cumbersome form of the equations, the modulus of the complex amplitudes is not presented in the paper. Based on the analysis of the obtained frequency response of the elastic system, we obtained the values of the disturbance frequencies at which resonance occurs in the system, both the resonance of the spindle's headstock, resonance of the tool, and the resonance of the table. Conclusions of the impact load frequencies were determined for a tool with a single groove on its work surface. In the article, it was investigated that under the thermodeformational treatment using a tool, high frequency with a small amplitude intense plastic deformation occurs, and the article presented that high-frequency deformation positively affects the formation of a nanocrystalline layer. To determine the dangerous rotational velocity of the tool and the grooves number of the disk peripheral at which resonance can occur, a graphical dependence of the resonance of the number of grooves was constructed. The dependence obtained showed that an increase in the grooves number of the disk peripheral reduced the velocity at its periphery at which resonance is possible. The minimum velocity at which the thermal deformation process occurs in 60 meters per second, resonance is possible if 11 grooves are on the tool's work surface at this velocity. Therefore, for the tool to operate normally, it is necessary to have at least 12 grooves on tool's work surface. The tool will operate under normal oscillation condition at frequency shift to the right of the system resonance. The open-loop frequency response was constructed to investigate the stability of machine tool elastic system. The obtained frequency resonance does not cover the point which coordinates -1, I0. The closed system is stable. A dynamic model of mechanical processes that take place during the thermodeformation treatment of machine parts with a tool with a discontinuous work surface have been developed, which allows to study of the frequency response of the system and according to which to provide recommendation for choosing the grooves number of the disk peripheral. Improvement of the physical and mechanical properties of stressed layers and their quality parameters can be obtained by using a tool with a discontinuous work surface, with a grooves on its working surfaces. The number of grooves should be such that it will ensure the processing process at frequencies higher than resonant. Thank you for your attention.
Thank you for your presentation. Are there any questions from the audience?
Yes, I'm Natalia Chernovol from Belgium. I have a small question concerning the achieved dimensions and the impact of the process on the dimension. Have you investigated it?
We made a theoretical, hello, first of all, we made a theoretical and experimental studies. And first of all, we saw it when we made our process of hardening. and we selected 8 grooves. And we saw that our system are near or very closer to resonance. And then we start to modeling and simulate our investigation and saw that really 8 grooves is very bad because they are very close to resonance. And our recommendation is to make our cutting tool with grooves that more than 12 pieces. And
But
we simulate in MathCAD if you ask about software.
Okay, thank you very much for your answer. But I think I will better formulate my question. So, if you increase the number of grooves, do you see an impact on the dimension? Okay, you went out of resonance, but then I would expect that there will be also some impact on the level of deformation and as well the dimensional accuracy afterwards.
Yeah, you're right. When we thought first of all when we increase and okay, I will maybe come back to and tell that first of all we saw that when we made these grooves, our shear deformation increased. And the main idea is to make a lot of these grooves to increase shear deformation. But we made very nice simulation where we made a theoretical experimental studies of thermoelasticity. And these modulations help us to determine a value of heating the temperature of contact zone and a cooling in this contact zone when our groove is escape of our contact zone. And our simulation of thermoelasticity show us the maximum grooves that we can produce in our periphery of tool to make a nice nanocrystalline structure. I mean about quality nanocrystalline structure. And when you ask about how much should be these grooves, more than 12, but not more than 32, because another simulation show us a maximum of grooves that should be in our tool.
Okay, thank you very much for your answer. Maybe that's something to consider for a further study as the impact on the surface patterns and these kind of things. Okay, but thank you very much.
Thank you.
That was it from my side.
Thank you, Natalia, for your questions. There are any questions? Okay, now we are taking a break and we will resume at 3 p.m. See you in 3 p.m.
Thank you. See you soon.
Первых.
Let's begin. Okay, we continue our first section, digital and intelligent manufacturing engineering. Now I'd like to invite Дмитро Павленко, Юрий Торба, Игорь Федоров, Евгений Вишнепольский и Лариса Тумарченко to present on the topic of enhancement of surface layer resistance, stress distribution, and surface roughness in titanium 6, aluminum 4, vanadium components using high-speed milling and vibro polishing. Okay, I share my screen.
Dear colleagues, I am pleased to present the results of the study aimed at improving the surface layer quality of titanium 6 aluminum 4 vanadium titanium alloy parts manufactured using additive technologies and solid phase metallurgy methods. The research focused on identifying the irregularities of residual stress and surface quality formation through the integrated use of high-speed milling and vibratory polishing. Titanium alloys, especially titanium 6 aluminum 4 vanadium, are widely used in aerospace engine manufacturing due to their high specific strength. However, their machining presents a number of challenges, including low thermal conductivity, high adhesion to cutting tools, and the tendency for strain hardening. All these issues are inherent to titanium in the submicrocrystalline state, but to an even greater extent. The study of surface layer quality after processing was carried out on full-scale compressor blades of a small-sized gas turbine engine. The blade blanks made of VT6 and VT8 titanium alloys were produced from a mixture of powder components based on titanium powders, followed by intensive consolidation using the technology described in detail in previous works. The blade airfoil shaping was performed using the spiral high-speed traverse milling on a 5-axis machining center Hermel model C4U dynamic. For finished cut-down high-speed milling, end mills made of BK10XOA material were used with the following geometric parameters: cutter radius 4 mm, number of teeth 4, rake angle 20 degrees, clearance angle from 2 to 6 degrees, helix angle 36 degrees, milling depth 0.5 mm, line width 0.5 mm, and tool axis tilt angle 6 degrees. The cutting edge radius after sharpening was from 0.05 to 0.1 mm. During milling, the cutting fluid was supplied to the cutting zone under pressure. The blade airfoil polishing was carried out using a vibratory method on a Rosler R220 EC circular vibratory machine. The blades were placed into the working chamber of the machine without fixing, which was filled with abrasive filler, ceramic abrasive particles. RMBD1 1015S abrasive granules were used as the filler. The polishing time was 5 hours. The investigation of residual stresses in the surface layer of the blade airfoils was carried out using the method of drilling small holes, in accordance with the standard of the American Society for Testing in Materials ASTM E837. The measurements were performed using the Synthrostron MTF 3000 system from Italy, which was a part of the integrated residual stress measurement system. The use of the drilling small holes method allowed to determine the stress distribution in the surface layer at various points on both the pressure and suction sides of the compressor blade airfoils, such of which didn't exceed 20 per 20 mm, widely used in the design of small-sized gas turbine engines. High-frequency drilling modes were used, allowing the influence of the drilling processes on the measurement results to be neglected. The strain gauge sockets were attached to the suction side of the blade airfoils, and then the high-speed drilling was performed with simultaneous recording of surface deformation in 3 directions and simultaneous calculation of the in-plane stress state components. The stepwise drill feed with a 10 micrometers increment allowed to study the distribution of residual stresses in the surface layer to a depth of up to 200 micrometers. The slide illustrates the manufacturing process of parts made from titanium alloy semi-finished products obtained by powder metallurgy methods, followed by plastic deformation using severe plastic deformation techniques. This process includes shaping the main surfaces through machining, as well as applying surface finishing and strengthening treatments. Microstructural analysis using an optical microscope revealed that screw extrusion led to the refinement of structural components. However, it was not possible to determine the grain size as the given magnifications. The formation of deformation texture during extrusion was confirmed by the pronounced alignment of structural elements along the direction of blank movement. To establish the regularities of residual stress state formation of the surface layer depending on the milling modes, a full factor experiment with 2 independent factors varied at 2 levels was realized. The ranges of mode parameters variation were cutting speed from 62 to 314 meters per minute, feed per tooth from 0 to 0.05 to 0.15 mm per tooth. Taking into account that the main mode parameters influencing the quality of the surface layer could not be measured and controlled explicitly, the milling modes determining them were taken as factors: x1, the number of machine spindle revolutions measured in RPM, x2, the minute feed rate of the cutter measured in millimeters per minute. To exclude experimental errors, each experiment at a given level was repeated twice. The results of duplicate experiments were averaged. The experiment planning metrics and the obtained values of response functions are presented on the slide. The diagrams of residual stress distribution in the surface layer after high-speed milling with the different modes showed that the investigated range of cutting modes compressive residual stresses were formed in the surface layer. The maximum value of residual stresses was observed at a depth of 25 to 35 micrometers from the surface, didn't depend on milling modes, and was about 260 to 350 megapascals. The analysis of variance of the active experiment results allowed to study the influence of cutting speed and feed rate per tooth on the value of residual stresses. It was found that the investigated cutting modes, as well as the apparent interaction, had a statistically significant effect on the value of residual stresses. The greatest influence was exerted by the cutting speed. The influence of cutting speed and feed was multidirectional. Increasing the cutting speed led to a decrease in the value of compressive stresses, while increasing the feed rate per tooth was accompanied by their increase. Analysis of the response surface of the investigated value showed that the effect of cutting speed, contrary to the feed rate per tooth, is non-monotonic. Thus, increasing the cutting speed is in the range of 63 to 190 meters per minute was accompanied by 30–35% decrease in the value of compressive residual stresses. Further increase in cutting speed was also accompanied by a decrease in the value of compressive residual stresses in the surface layer. However, their value was decreased by 5 to 7%. In the range of feed of rate variation of 0.05 to 0.15 mm per tooth, the value of compressive residual stresses monotonically increased by 15 to 19%, depending on the cutting speed. The observed regularity was explained by intensification of the thermal factor of residual stress formation as the cutting speed increased and the force factor as the feed increased. The results of the regression analysis are presented on the slide. To assess the statistical significance of the regression equation coefficients, the variance of each trial was calculated and the homogeneity of the variance series was checked by the coherent test. The surface roughness of the pressure and suction sides of the compressor blade airfoil after high-speed milling varied within array 0.36 to 0.48 micrometers depending on the processing modes. The surface profile of the blade airfoil was typical for the parts processed by high-speed milling and clearly expressed transverse stitching. To eliminate them and to ensure the required roughness value, it was necessary to perform the subsequent polishing operations. Thereby, based on the study results of the surface layer quality parameters and surface of blade airfoil during processing by high-speed milling, it was established that the processing mode should be assigned based on the stage, roughing, semi-finishing, and finishing. Considering that the purpose of roughing and semi-finishing milling stages is to ensure the required value of shape accuracy of aerodynamic surfaces, the milling mode for them should be determined by the maximum productivity of machining. Moreover, at the semi-finishing stage, a reduction in cutting speed and feed rate leads to a decrease in cutting forces and an increase in the accuracy of the shaped blade surfaces. As the finishing stage of milling, the molds are selected based on the requirements for ensuring the quality of machining. The peculiarity of HSM alloys in submicrocrystalline state is also the need to consider the possible recrystallization of grains in the surface layer under the action of cutting temperature. The table presents the rational cutting modes for HSM of VDA type alloys in a submicrocrystalline state. Considering the established regularities of quality parameter formation of blade airfoils during HSM, the cutting depth is set depending on the cutter diameter and, for roughing and semi-finishing, considering the low stiffness of the compressor blade, and ranges from 4 to 6%. For finishing, its values doesn't exceed 1 to 2%. Vibro polishing of the compressor blades allowed to completely remove the regular micro-relief stitching from the previous high-speed milling and provide surface roughness within array 0.18 to 0.22 micrometers for the pressure side and array 0.22 to 0.36 micrometers for suction side. Therefore, the finishing processing of the sample surface provided improvement of the surface layer quality. It was determined that vibro polishing with a rational combination of mode parameters resulted in a significant enhancement of residual stress level within the surface layer of the specimen. Based on the analysis of the established regularities, rational modes of the technological process were determined. High-speed milling induced compressive residual stresses in the surface layer regardless of mode, with the maximum values observed at a depth of 20 to 40 micrometers. For optimal productivity, roughing should be performed at cutting speeds of 160 to 180 meters per minute, with a feed rate of 0.05 to 0.1 millimeter per tooth, while finishing at 100 to 120 meters per minute with 0.15 to 0.2 millimeter tooth feed induced compressive stresses of 380 to 390 megapascals. High-speed milling formed transverse lines on the surfaces, which were removed by 5-hour vibro polishing, resulting in a surface roughness of 0.18 to 0.22 micrometers. Future research will focus on assessing the micro-hardness distribution after finishing strengthening, as both residual stress and deformation distribution affect the load-bearing capacity of parts under variable loads. So that's it for the presentation. Thanks for your attention.
Thank you. Thank you. It was very interesting and informative presentation. Are there any questions from the audience? Okay, I have a question. What physical mechanism determine the multi-directional influence of cutting speed and feed per tooth on the level of compressive residual stresses in the surface layer?
Okay, can you hear me?
Yes.
Okay, good. So in titanium alloy machining, cutting speed and feed rate have opposite effects on residual stresses. Higher cutting speeds reduce compressive stresses due to increased heat generation, causing thermal softening in the surface layer. And in contrast, higher speed rates enhance compressive stresses by increasing mechanical force and work hardening. That's it for this question.
Okay, Natalia.
How changes in roughness and residual stress levels after vibration pollution can affect fatigue strength?
Okay, thank you for your question. Vibro polishing improves fatigue strength by two factors. The first one is reducing surface roughness, eliminating stress concentrators that initiate cracks. And the second one is enhancing compressive residual stresses in the surface layer, creating a mechanical barrier against crack propagation. So these two combined improvements help titanium components better resist cyclic loading. That's it for this
Thank you.
question.
Okay, thank you.
Now I would like to invite Сергей Кононенко, Сергей Добротворский, Евгения Басова, Дмитро Trubin, and Rafal Talar to present to the topic of impact of overlapping methods of cutting forces and surface formation and milling of think wallet parts.
Hello everyone! Today I will present our research on the impact of overlapping method on cutting forces and surface formation in end milling of thin-walled parts. Thin-walled parts are critical components in aerospace, automotive and precision engineering, but their machining presents serious challenges. During conventional end milling, passes are performed around the part, declining toward the base. It offers high accessibility as many CNC setups and tool paths are optimized. However, these parts often experience large deflections, especially near the unsupported ends. This results in low surface quality, which frequently requires additional fixture supports and increasing cost and complexity. To address these limitations, the research explores the overlapping method, where successive tool paths partially cover previous ones, aiming to improve material removal and surface finish without needing extra support structures. The aim of this research is to reduce machining errors by studying how overlapping scallop passes affect the structure and surface quality of thin-walled parts. Specifically, we investigated how actual deflections behave at different fractions of overlapping, the relationship between scallop height and roughness, how cutting forces, especially the horizontal component Fy, respond to tool lead angles, and whether this method enables a more stable mechanical interaction. The focus is on enhancing accuracy by strategically adjusting the overlap fraction and tool positioning without changing the fundamental machining setup. To study the effects of overlapping method, we used a combination of geometric modeling and finite element simulation. The overlapping method is carried out within a linear ball end milling framework using an equidistant tool path, where each pass follows the previous one with a defined overlap, which is a key for forming specific scallops on the surface. We incorporated the rigid representation into the flexible one by defining the actual scallop height parameter. Finally, we compared the overlapping and conventional meeting, focusing on 60, 75 degrees two lead angles to observe their effect on mechanical performance. We analyzed how different overlapping fractions 25, 50, 75, 100% generally affect forces and stresses, especially on the flexible structure to get the deflection value delta max. The actual scallop height is defined, which is dependent on the overlapping value lambda. Using finite element method, we measured structural deflections delta max to estimate roughness that accumulates the surface deflection due to uncut scallop height. The simulations included Johnson-Cook plasticity and damage models, and due to material strength, plasticity, and damage constants, accurately reflect how IEC 4340 steel behaves under high-speed milling conditions. We carried out detailed simulations to observe how overlapping scallop passes impact the part behavior depending on the overlapping fractions. This slide shows the result of full overlapping in the milling process. The tool fully overlaps the previous scallop pass, which leads to much more uniform contact with the surface. The actual residual scallop height in this case was reduced to 11 microns. In contrast, this slide shows the effect of only 25% overlapping. Here, the residual scallop height remains high, about 157 microns, which leads to uneven force application and more aggressive cutter impact. This configuration increases the horizontal force component Fy, which acts in the direction of minimum stiffness, making the wall vulnerable to bending. Considering the graph on the left, it is noticed that with every 100 microns decrease in scallop height, the horizontal force Fy drops significantly. What can be estimated from the graph on the right? As the degree of scallops overlapping increases from 25 to 100%, the surface roughness decreases from 114 to 63 microns, indicating the residual scallop becomes smaller. Generally, the lower overlapping, the higher roughness. The higher overlapping, the lower force impact on the wall. The graph can be divided into three parts: an increase in the horizontal force component Fy, slow down, and decrease. This behavior reflects the relationship between the resistances generated by the immersion regions and the tool cutting edge. At full overlapping, the Fy force was 27.5% lower compared to the conventional method. This showed effectiveness of overlapping in the reduction of the stress on the wall. We also observed a more stable mechanical interaction because as the tool entered the scallop structure, the chip load increased gradually, which avoided abrupt force spikes. Additionally, surface roughness dropped from 114 to 63 microns, as the overlap increased from 25% to 100%. From the simulation results, we saw that 60-degree lead angle in comparison to 75 gave the best force reduction, aligning better with the direction of maximum stiffness of the part. Generally, the overlapping clearly minimized static deflection and generated more uniform stress fields compared to the conventional approach. To summarize, our research confirms that the overlapping method provides notable advantages over the conventional. By gradually increasing overlap fraction, we observed a reduction in horizontal cutting force component, especially applying 60-degree lead angle. Surface quality also affected at the highest overlapping fraction. The residual scallop height dropped to 11 microns, and the roughness also decreased, which potentially contributes to better topological performance. Importantly, this was achieved without any additional fixture supports. Finally, the overlapping method promotes more stable mechanical interaction, aligning cutting forces with the stiffer direction of the part. These findings point toward a reliable strategy for improving machining accuracy and functional surface performance in thin-walled components. Thank you very much for your attention.
Thank you for your presentation. There are any questions from our audience? Okay. Mike.
Yeah, sorry, just from my side. The conventional lead angle, what was the consideration there if we consider the 0 degrees in the feed direction?
Thank you for the question. Yes, in the context of conventional milling, we performed simulation with the 0 degree angle and compare it to overlapping method with 75 and 60 degrees tilt angles.
But do you make a comparison between the lead angles and then you also, as a conventional method, define the different tilt angle? So you change 2 factors at a time. What's the idea behind, if I may ask?
Yeah, the idea behind is to compare, first of all, 2 methods, the conventional method and the overlapping one. And in the context of overlapping, we compare 2 degree tilt angles. So the major point is to show that the overlapping method could bring some better cutting conditions.
Yeah. I'm a representative from the industry, so I'm looking at things a bit from the practical perspective. If we are looking on the way it has been performed, then if you are changing the tilt angle so significantly, it can be the case that the operation on the milling machine cannot be performed due to the collision issues or the interaction with other surfaces of the part. So how did you consider this aspect?
Yeah, thank you. We considered the performance of cutting for the separate example of part. So it's a thin-walled part separately without any additional parts around. Of course, conventional method is appropriate more in case when it's kind of turbine blade and have a lot of blades, and CNC system is set for this kind of operation, but we consider some kind of novel approach and in some applications, some thin-walled parts could be processed in that way because they have no additional in the space other thin-walled parts, and we can perform it just tilting the angle and cutting the scallops obtained at the stage of previous machining.
Okay, it's clear. Thank you very much for your answer.
Thank you.
Thank you, Sergey. Now I would like to invite Sergey Dядя, Mikhailo Frolov, Sergey Tanchenko, Vasily Salocha, and Denis Sakhno to present on the topic of feed rate influence research on the machined surface waveness parameters in end-up milling of thin walled parts.
My name is Mikhail Frolov, and I represent report research of the feed rate influence on the machine surface waviness parameters in the end-up milling of thin-walled parts. The study was made at the Zaporizhzhia Polytechnic National University, Zaporizhzhia, Ukraine. Today, about 75% of the metal cutting tools market meet the needs of such high-tech industries as aerospace, automotive, and defense. And almost a third of these metal cutting tools are various milling cutters. All above industries use thin-walled parts because of the construction features and need of weight reduction. But at the same moment, they meet the big challenge because of vibration caused by the lack of internal rigidity. At the same time, we need to stress the point that macro relief of these parts is more important than micro relief because it affects part positioning and function. So we need to take big measures to eliminate influence of vibrations on the parts quality. In previous studies, it was found that vibration phenomena directly depends on belonging to one of the vibration speed zones. Belonging to one of these zones defined by DR, defining ratio, which is the ratio of time of cutting to the period of natural vibration. We analyzed this data regarding influence on the macro relief, namely waviness, and means of vibration reduction. So the first zone is characterized by low efficiency and no waviness is observed here, but milling is not reasonable due to low efficiency of milling in this zone. The second zone also characterized by low efficiency, but we see some damped vibration with an amplitude up to 0.2 millimeters. Micro relief is better than in zone 1 and slight waviness appears here, but milling also not reasonable here. The third zone is characterized by damped vibration with an amplitude of more than 0.2 millimeters. Surface quality is better than in zone 2, but the significant waviness appears, and the mean of vibration reduction is the choice of rational cutting conditions in this zone. Fourth zone is the part of high-speed milling. No vibration specific for zone 2 and 3 are not observed. And macro geometry is formed by the forced vibration. And to eliminate vibration in this zone, we need to use special damping techniques. Resuming previously said, the objective of this research is study of the formation of waviness under the influence of vibrations given their physical nature. The purpose of this study is to determine the influence of vibrations on the parameters of machine surface waviness during and up milling in the third vibrational speed zone, and the role of one of the technological parameters in this process, a feed rate. You may ask why we choose the third vibrational speed zone. Since milling processes may be performed in the wide range of milling conditions, and the big number of productional processes will be made, namely in the third vibrational speed zone. Moreover, this zone is most problematic from the point of view of waviness formation. The tasks of this study is to conduct experimental studies on milling samples in the third vibrational speed zone with different feed rates, evaluate vibration characteristic and that of the waviness. Based on the obtained values, perform a statistical analysis of the effect of the feed rate on the vibration and parameters of machined surface waviness. Here we can see the construction of experimental setup and some brief information concerning materials, equipment, parameters, and conditions of this study. Analysis of the results obtained from the position of statistical significance of these results is based on ANOVA, which means analysis of variance, formula for which is shown in this table. One of the most important parts of this study is that during and up milling of thin-walled parts, the specific type of damping vibrations was met. These vibrations acted during the cutting time and was classified as attendant-free vibrations. On our opinion, exactly these vibrations are responsible for waviness formation. Here you can see the oscillograms of AFV at different feed rates and also the profile diagram of waviness. We chose several parameters for AFV characteristic and waviness as well. The first one is span of the AFV R2. You can see here on the diagrams. The second one is period of AFV. The third one is deviation from the elastic equilibrium position of the first AFV wave, delta. Here is it. And the height of waviness, W sub Z, and the pitch of waviness, S sub W. Several key features of attendant-free vibration. The first one is limited duration. They operate during time of cutting, followed by the natural vibration of the workpiece. The second one, triggering pulse. Distinctive first wave that, on our opinion, has a crucial impact on the waviness formation. The third one, surface transfer. Parameters transferred to machined surface. And the last one, zone 3 impact, most intense in third speed zone. Let's see the dependence of AFV and waviness characteristics on the feed rate as well as their statistical significance. The A figure shows dependence of AFV period and pitch of waviness as sub W on the feed rate. We see that these two dependencies have a similar character. B figure shows dependence of W sub Z, it's a height of waviness and delta deviation of the first wave on the feed rate. These dependencies also have similar character, and this dependence is statistically significant as well. The C figure shows dependence of R sub 2, its span of AFV on feed rate. According to ANOVA, the first dependence in the first 3 points are not statistically significant, but when the feed rate increases up to 0.3 millimeters, R sub 2 decreases statistically significantly.
Так, зараз чуєте мене? Звук є?
Є.
А на відео?
А на відео не було.
Так. Так, зараз звук є. Відео звук є. Окей. Так, I'm so sorry. Try again. I do my best. Так, зараз повинен.
So we introduced several indicators that characterize damping effect. The value of these indicators decrease when the damping effect itself is increasing. These indicators demonstrate very similar character as well as strong correlation. It means that our hypothesis is not rejected with a high probability. Here we demonstrate correlation metrics of AFV and waviness parameters. It shows that the period of AFV forms a pitch of waviness. Here you can see it. And the deviation of the first wave forms the height of waviness, as we suggested before. So, some resume concerning statistical significance. Variance analysis shows that feed rate effect is statistically significant. Correlation. High correlation is observed between AFV and waviness parameters. Waviness impact. Feed affect pitch more directly than height. And the last one, damping effect. Increased feed rate increases vibration damping. All above allow us to formulate the waviness formation mechanism. The first, initial cut. Cutting starts with smallest layer thickness and do not depend upon the value of the feed rate. First AFV wave determines waviness character. Surface transfer. AFV parameters transfer as heredity to machine surface. Waviness formation. Pitch and height form final surface quality. And finally, conclusions. Cutting starts with the smallest thickness. Conditions at the beginning of cutting are similar regardless of the feed rate. Statistically significant relationship between feed rate and the vibration parameters were established. With an increase in feed rate, the period and span of the AFV decreases. The change in the AFV first wave deviation has an extreme point. Increase in the degree of damping with feed rate increase. The first wave of the AFV determines the nature of the waviness during the end-up milling of thin-walled parts. The period and deviation from the elastic equilibrium position of the first wave of the AFV statistically significantly define the pitch and height of the waviness on the cutting surface, which are transferred to the machined surface as heredity. Dear colleagues, we appreciate your attention very much, and thank you for this possibility. Questions, please.
Thank you, Mikhailo, for your presentation. Any questions from the audience?
Yeah, Mihailo, first of all, thank you very much for a very nice presentation. So I have a few questions. First of all, I see that you have studied quite extensively the upmilling and the surface formation during upmilling, but do you see the same effect during the downmilling, but of the last, let's say, pattern of your time domain signal? Or of the last wave of your time domain signal?
Okay. I understand your question.
In down milling, there is no such effect. Effect of down milling will be a little bit later, but not like this. Absolutely different.
And what do you consider to be the main reason of such an effect during the upmilling? The initial impact?
Of this, you mean the main reason of this effect in upmilling?
Yes. Because why we see it in upmilling, but we don't see it in downmilling? What is specific for upmilling?
Sure. For downmilling, it depends at which conditions cutting starts. At upmilling, all the cutting, regardless feed rate, they are starting at the same conditions. For downmilling, it's different. The cutting starts at different conditions. So, and very important in this, for solution of this, for this issue is a very important starting conditions. It's like a first impact for waviness formation. So it's absolutely different effect.
Okay, thank you very much for the answer. And the second question from my side is, did you also consider the effect of the tool runout on the first wave and the surface formation?
First, excuse me, tool runout?
The eccentricity of the radial runout
yes.
of the tool, the eccentricity of the tool?
No. It's not was the problem. We paid attention at this very research. It's well, it was the main aim, objective of this research is to find this physical mechanism for waviness formation, and like additional factor, no, we didn't consider this.
Okay, then maybe the last question from my side, because you are talking about the waviness and the feed rates, but also here maybe isn't it also interesting to consider the roughness, or because waviness is a higher order degree surface form errors, so compared to the roughnesses, and then we also see a lot of effect of the dynamics on the surface formation and on the roughness values. So let's say if you see the volley due to the initial impact, then also throughout the milling of the surface, you have deviations due to the effect of the tool entrance, of the dynamic state, of the position of the part while the tool enters. Did you also consider these effects?
Effects on roughness, it's a different subject. We didn't concentrate it in this research on roughness because previous analysis shown for us that for functioning of the thin-walled parts, waviness is more critical than roughness itself. So we have some data about influence of these attendant free vibrations on the roughness, but they are not processed from the statistical point of view. So the great number of information, and I think it's a little bit later that we'll come to this issue also.
Thank you very much for your answer, and I'll be looking forward to your next research results.
Thank you for your questions.
Thank you, Natalia.
Ну, тут таке, що заготовлене.
There are any questions from audience? Okay. Now I would like to invite Яків Немировський, Валентин Атаманский, Игорь Шепетенко, Alexander Melnik, and Yaroslav Stepchin to present on the topic of simulation of the forming scheme during deforming broaching. of parts with through deformation.
Feature of the deformation zone scheme during deforming broaching of part with through deformation. Яків Немировський, Валентин Отаманський, Олександр Мельник, Ярослав Степчин, Ігор Шепеленко. Deforming broaching is a process of cold plastic deformation of a workpiece hull. According to this process, a tool, a deforming broach or broaching piercers, move along the hull of the workpiece according to a kinematic sliding pattern. The scheme of the deformation zone is one of the main issues when studying the process of deformation broaching. The known scheme of deformation zone consists of a contact area 2 and 2 non-contact zones 1 and 3 connected to it. Paper 10 describes a theoretical model of the deformation zone for the distribution of thin-walled shell-type workpiece T0 over R0 less than or equal to 0.1. As shown by the results of the calculated and experimental data, Figure 2, the axial dimension of the non-contact zone calculated by the model increase monotonically with increasing wall thickness and coincide well with the value of experimental data. At the same time, when determining the contact length and the height outside the contact zone behind the contact area, car 1, 4, the coincidence of the calculated and experimental result is observed only for the case of machining steel-walled workpiece. Therefore, the result obtained according to the model are valid only for the formation of thin-walled parts. The purpose of this study is to determine the feature of the tool workpiece interaction scheme during deforming broaching of workpieces made of plastic materials in a wide range of change in their thickness under through plastic deformation. Achieving this goal requires solving the following tasks, which are presented on the slide below. The stress-strain state modeling of an axisymmetric workpiece made of plastic materials during deforming broaching was performed in the Deform 2D/3D software. The simulation considered the machining of two workpieces with the same internal diameter. The inner diameter of the workpiece is D0 equal 40 mm. The outer diameter of the first workpiece is D01 equals 44 mm. And of the second, D02 equals 68 mm. The length of the workpiece is h equal 150 mm. The deforming element is made with a working cone angle alpha equals 4 degrees. The diameter of working element is dE equal 41 mm. The displacement speed of the deforming element is V equal 0.8 mm per second. The material used for the study is 12H3R steel. The chemical composition, mechanical properties of which are presented in reference 15. The developed model make it possible to analyze the stress-strain state at 3 points. Figure 3, Part A. Figure 4. Dependence of the change in strain rate during deformation of 12HN3R steel workpiece with tension on the element A over D0 equals 0.025. Angle alpha equals 4 degrees. T0 over D0. A 0.05, B 0.35. Figure 4 shows that intense deformation is observed when the contact area translation to the non-contact zone behind it. Obviously, there is a zone of local plastic deformation here. The strain rate increases to a value of Xi equals 0.03. With an increase in the thickness, figure 4b, the contact pressure increases and it begins to exceed the critical pressure. This affects the change in strain rates. The appearance of two zones of local plastic deformation at the beginning of the contact zone and at its end is clearly visible. In this case, the value of local plastic deformation is higher than during the deformation of thin-walled parts and reaches Xi equals 0.04 at the beginning of the contact zone and Xi equals 0.08 at the end of the contact zone. The simulation result, figure 5, show that the change in the generative function for the thin-walled part, curve 1, is smooth and differs from the change in the generative function for the thick-walled part, curve 2. It should be noted that the height of the non-contact zone behind the contact zone for the thin-walled part is significantly higher than the height of the non-contact zone for the thick-walled part, and the length of the contact area for the thick-walled part is significantly longer than for the thin-walled part. As follows from figure 5, curve 2, the contact zone has two areas of local plastic deformation. For clarity, curve 2 is presented in an enlarged scale. To confirm this fact, consider figure 6. As follows from figure 6, which shows the areas outside the contact zone after the tool working on a thin-walled workpiece, figure 6a, there is no contact of the cylindrical belt with the machine surface. As the thickness increases, the contact pressure increases, which causes the appearance on an axial flow of the processed material from the contact zone to the non-contact zone. This is evidenced by the appearance of contact between the processed materials and the cylindrical belt, figure 6b. And further increase in thickness leads to an increase in contact load and more intense flow of materials from the contact zone. The performance study of the deformation zone made possible to clarify the known scheme of interaction between the tool and workpiece, Fig 7a, and to establish the appearance of local plastic deformation zone, as well as change in the geometry of non-contact zone flow of the deformation zone during machining of thick-walled parts. This change is expressed in the flow of the processed materials from the contact zone to the non-contact zone, figure 7b. Figure 8a shows a change in contact length as a function of workpiece thickness when using different tensions. It follows from figure 8 that with an increase in the thickness of workpiece, the contact length first decreases and then begin to increase, with a clear bend in the function in the region of the critical wall thickness. It is clearly seen that the value of the critical wall thickness depends on the tension on the element and the angle alpha. Figure 8b. The figure shows
along with the calculated result, the experimental data obtained using a well-known technique. Reference 19. The value of the critical wall thickness at which the critical contact pressure, reference 20, occurs in the contact zone is determined by depends as shown at the bottom of the slide. As for the length of non-contact zone behind the contact area, its calculated value is shown in figure 9 car 1. In its form is particularly does not differ from the theoretical dependency for the determining this parameter figure 9 car 2 taken from figure 5 and obtained from the model for thin walled workpieces built on the basis of variational principles, reference 11. A methodology for studying the stress-strain state using the deformed software Pascage has been developed by modeling the deforming broaching of 12 H-N3A steel workpiece with different thicknesses and broaching modes and tool geometry, the feature of the tool-part interaction scheme during the stress-strain state of workpiece made of plastic materials in the presence of serous plastic deformation were determined. It is established that during deformation broaching under condition of critical contact pressure, zone of local plastic deformation occur at the junction of the contact area with the non-contact zone. For this case, the well-known scheme of the deformation zone at deforming broaching is refined. The reason for the local plastic deformation zone appearing, which become noticeable in the presence of the critical contact pressure, are explained. In this case, the front local zone in an influx of material from the contact area and increases its length. The rear local zone is a step of the processed materials that flow out of the contact area under the influence of the critical contact pressure and reduce the height of the non-contact zone. Theoretical experimental confirmation of this local plastic deformation zone exists tensed and presented.
Thank you. Your presentation. Are there any question from the audience?
May I have a question?
Okay.
Do you make a research about using some of lubrication and used it to stress-strain state?
I am understand this question. It is possible to do this. It is necessary to make algorithm for calculation the workpiece dimension after deformation, and then make a program according to the algorithm for a personal computer.
Okay, thank you.
Okay, Natalia, do you have question?
Yes, I have. Are further improvements to the technology plant taking into account the influence of temperature or cycle clocks?
I am understand this question. It's planned. After deforming, piston pins are subjected to chemical heat treatment. In order to obtain a normal structure that will provide improved part performance under cycle loads conditions, it is necessary the resource of used plastic after deformation should not exceed 30% of the total plastic resource. Therefore, we need further investigation the resource of used plastic during the deformation of piston pin.
Thanks.
Thank you, Yakov. There are any question? Okay.
I have one question, if possible. Okay.
Okay.
Okay. First question: what angle will be to optimize for your research? You study many angles, but what angle you recommended to use?
We recommend the technology process.
Ну, окей, thank you very much. Okay, no problem.
Ми можемо на український запитати, може.
Будь ласка, будь ласка.
Давайте.
Будь ласка, да. То мене цікавить, який угол у вашому інструменті ви рекомендуєте для оптимальної обробки. Тобто від вашого угла, угол то є функція змінна.
Да. Все залежить від того, що ми хочемо отримати. Якщо ми хочемо отримати осьові деформації стиснення, то угол рекомендується 2 до 3 градусів. Якщо ми хочемо отримати нульове змінення длини, то угол десь також 2 градуси. А якщо подовження, то угол 8 градусів. То в залежності від того, що ми повинні отримати, ми назначаємо угол. Ці дослідження проведені і будуть доложені на слідуючій конференції.
Дякую. І ще одне питання. На рисунку 5, на 5-му слайді у вас є зміна deformation, така дуже різка. Чим це можна пояснити?
Зараз покажіть, будь ласка, 5-й слайд, щоб я не...
Та вони ж не покажуть, мабуть.
Зараз вімкну.
Да. Фігура 5. Фігура. О!
Це...
П'ятий. Оцей?
Ні,
от був перший, що ви показували.
7-й.
Оцей, так.
Це показано, бачите, синім показано, як ми працюємо в області тонкостінних деталей, де немає контактних давлень, де контактні давлення контактні навантаження незначні. Там іде плавна лінія синя і проходить саме деформування в осередку деформації. А от красна – це угол 8 градусів. Що відбувається при цьому на 8 градусах? Там появляється в зоні контакту, матеріал витікає з зони контакту. Вон, бачите, такий уступ. Це він увеличує свою ширину контакту, і тут збільшення, виходить, витікає на циліндричну ленту. Тобто, происходить течія матеріалу з контактної зони. І там уже появляються оці піки, показані на рисунку 4, які свідчать по появу розтягуючих напружень, які дуже негативно впливають.
Добре.
Бачите, оце контактна дуже негативна.
Так. Дякую. Добра відповідь, добра. Дякую.
Дякую за вашу відповідь.
Да.
А,
Я дякую за ваші питання.
Добре.
Now I would like to invite Богдан Модрик, Олексій Подобний, Дмитро Павленко, Вадим Закиев, and Dmitro Lysyak to present on the topic of surface quality and wear behavior of aviation nickel alloy after wire ADM and ultrasonic fissioning.
Dear colleagues, I am presenting to you our report entitled Surface Quality and Wear Behavior of Aviation Nickel Alloy After Wire Electric Discharge Milling and Ultrasonic Finishing. Our research team united the researchers from Institute for Metal Physics, National Academy of Sciences of Ukraine, 3 Ukrainian universities, namely Zaporizhzhia Polytechnic, Kyiv Aviation University, and Igor Sikorsky Kyiv Polytechnic Institute, and the state enterprise Yushchenko Progress. Searching for effective methods for engine parts production is a very timely task. It is well known that engine contains numerous parts of complex shape, like the blade shown here on the right, and thus the problem of finding the high-performance methods for shaping these parts is relevant. One of the promising methods is innovative wire electric discharge milling using computer numerical control machines. However, the main issue with this method is high surface roughness and deteriorated properties of the VDM-produced parts. Therefore, the present work aims to investigate the surface micro-relief, microstructure, residual stresses, and wear resistance of nickel alloy after WEDM and finishing modification by high-frequency mechanical impact treatment. Wire electric discharge machining is known innovative method. This is an electrothermal machining process for electrically conductive materials. The scheme of the VDM process is shown on the left here, and on the right is shown examples of EDM machines. The main factor that hindering the development of this technology is the surface roughness and decreased properties of the parts after EDM. Since the surface roughness depends on the energetics of the process, we used in our study 3 energy regimes: light, middle, and hard regimes for EDM, and this process was performed on the facilities of Yushchenko Progress Enterprise. Further, subsequent surface modification was used by high-frequency mechanical impact treatment, which is efficient technique for hardening and relaxation treatment of metallic materials. Additionally, the surface roughness can be significantly reduced. This slide shows several schemes of the FMI process on the left, and on the right you see the example of the facility on the design bureau aging progress. This is the vibration chamber with metallic balls used for treatment of complex shaped parts like blades, engine blades or compressor blades. The main advantages of this treatment is the flattening of the surfaces, nanostructuring of surface layers, and compressive residual stresses. In this study, we used the ultrasonic treatment, portable one, and its parameters and the regime is shown in this slide. The chemical composition of the studied nickel-based alloy is shown on this slide. We used optical interferometry and scanning electron microscopy to investigate surface topography and roughness of the samples. Mechanical properties was assessed by instrumented indentation technique, and the resistance was evaluated using repeated scratch tests. Considering surface morphology of the samples after electric discharge milling and following a frequency mechanical process, we can conclude that in comparison with the polished sample, the surfaces after EDM process became much rawer. So the higher the energy used, the larger the surface roughness. Fortunately, finishing surface modification by high-frequency mechanical input allows significantly reduce the surface roughness. It is important because we avoid the stress concentration on the surface relief and thus can prolong the operation life of the material. This conclusion was confirmed by scanning electron microscopy observations. On this slide, you see the morphology of the surface after light in EDM process, middle and hard EDM process. The highest roughness is observed after higher hard EDM process. Fortunately, surface roughness and surface morphology is much smoother after finishing using ultrasonic equipment. Here on this slide, you can see the numerical parameters of the surface roughness. Again, we see that comparing to polished sample, EDM process increase the roughness, and following surface modification by finishing treatment using ultrasonic instrument essentially reduce it. We can observe the hardness changes using indentation method, and it is shown that the hardness changes occur on the depths up to 35 micrometers, and after light regime we have some hardening, while the hard regime results in softening of the surface layers, and finishing FMI process can restore the hardness and even improve it. Finally, regarding the wear resistance, we used the repetitive scratch tests. When the subsequent 7 scratches were performed on the same track, and this scanning profilometry was used to assess the depth of the track, of each track. Also, observations of the views of these tracks were obtained by optical and scanning electron microscopy. Here we can see the polished surface and the surface after light EDM process. The results is here. On the left, we see that in comparison the polished material, the depth of the scratch tracks is much higher after EDM, indicating the worse wear resistance. However, after finishing deformation treatment, we can restore the wear resistance by equalizing the depth of the polished and EDM processed materials for regimes light and middle. However, the hard regime need more intensive deformation process, and the regime should be determined further. So we can conclude the following. The results obtained indicate that the choice of the EDM process should be made taking into account the required production productivity and a number of factors affecting the heat affected zone and material state, surface roughness, mechanical properties, state stress, and contamination. High frequency mechanical impact using ultrasonic instrument essentially reduces the surface roughness, which is beneficial in terms of the improved operational properties. Wear resistance can be restored and improved by surface modification, and therefore the wire electric discharge milling process can be effective for shaping complex profile surfaces of gas turbine engine parts, provided the optimal modes and wire materials should be made. And high frequency mechanical impact is a feasible treatment for finishing surface modification of the nickel-based aviation alloy parts and gas turbine engine in general. Thank you for your attention.
Thank you, Bogdan, for your presentation. There are any questions from the audience? Okay, I have a question. What are the main technological changes that occur in the surface layer of nickel alloy after wire ADM using different types of wire?
Thank you for the question. We used in this study two types of wires, and this was brass wire and molybdenum wire. And regardless the wire used, the EDM process results in the increase on surface roughness accordingly. Considering the changes in the near surface hardness, in both cases, it can be concluded that the microstructure, including the grain size in the surface layers, are changed, and maybe if energetics of the process is high, the grain size is larger, and that's why the hardness is lower. At the same time, the main difference observed between this wire use is the chemical composition of the surface layers after VDM process. If we use the brass wire, we observed that the chemical composition changed significantly, and the content of this copper and zinc enlarged after process. This can be deteriorative to the properties of the material because changing in the chemical composition can change the properties. And fortunately, if we use the molybdenum wire, then we observe no changes in the chemical composition. That's why we recommend the, namely the molybdenum wire to use in VDM process of nickel-based alloys.
Thank you. Natalia, do you have question?
Yes. How does high frequency machining affect the performance characteristics of the alloy?
Thank you. Based on the results of our study, we can make conclusions regarding only the wear performance. However, generally, we know that our process that we used here can enhance many surface-related properties, such as wear resistance, corrosion resistance, fatigue resistance, and the main reasons for this enhancement relates to several factors that we study in this work. This is a diminishment of surface roughness, the compressive residual stresses, and increasing the hardness. And to the end of this study, we can say that hardening that we provide due to finishing ultrasonic process provides the higher wear resistance of the material.
Thank you.
You? Are there any question?
Yeah, from my side.
Okay.
Go forward.
Please, Natalia.
Okay. Nowadays, we see quite a big tendency towards the hybridization of the processes. So connecting two processes in one machine. And there was recently also a study of the hybrid process with EDM in ECM, also allowing to improve, first of all, the productivity of the process, but also the surface finish quite significantly. So have you ever considered to make a hybrid installation? Is it a possibility?
We have our handle equipment that can be robotized. And we have some experience in this moment because our colleagues from Canada use our equipment in some robots to provide more uniform treatment of some metallic surfaces after their production. That's why I hope that we have some expectations that our process can be integrated in some hybrid process.
Okay, thank you very much. I think my question was more about, can we integrate the ultrasonic post-processing in a wire EDM machine?
I think that it would be better to use some equipment after obtaining the product, because especially if it is a complex shape product. However, maybe if we use some equipment, I think that there will be different equipments. I show some schemes on third or second slide, where we use ultrasonic devices with chambers and balls, metallic balls, that we can use for complex shape materials. And other scheme can be used when we obtain some cylindrical parts, and then we can use also these ultrasonic devices in repair.
Thank you very much for your answer.
Sergey,
Okay.
please.
No. Maybe I don't know very well this method. More simple, you discussed about this method. I don't understand how it's to realize this method. Where, what diameter of this wire, and moving this wire is in normal position to detail.
As I show in one of the slides, it
Maybe
is,
at the second slide.
yes, scheme of the EBDM method. The wire can be of different diameters, and it depends what the energetics of the process. If we use too low diameter, it can fracture, and we can obtain our product. Especially, I think that there are many industrial devices and equipment is regarding the wire EBDM process, and we just use the finishing in our institute. We use the finishing process, and the samples we obtain from our colleagues from the Progress Enterprise.
Oh, okay, stop. Да. When we see on your scheme, we will see this your wire take contact with your detail.
Here there are no wire, because it is the schemes for finishing process of the product obtained by the EBDM process shown on the previous slide. Can we see previous slide, Pane Pavlo? Yes. Here you can see on the left the scheme for this process. Wire that is moving in a perpendicular direction to the piece. Between the piece and the wire is the electric current, and the spark between the wire and the piece.
I understand this spark process. Okay, I understand.
Yeah.
And if possible, last slide.
Next.
No, on the end. Oh, this. No. What?
Last. Okay, last.
It's no last.
Next, please.
Before
Next.
last. Before. Oh, this. Да. In your result, maybe I don't understand. Polishing surface, it's not very well for use. Okay.
We just use the repetitive scratch test. When we scratch,
I understand, but level scratch test, it's very higher on polish surface.
The curve with the black squares, it is the polished surface, and each square relates to the each scratch. And when we repeatedly scratch the surface polished, we obtain the initial depth, which we compare all other our materials, our states. That's why on the right, in figure B, we see that this initial polished material the same as the finished at the end processed material.
I
And
understand
that's
you.
why we conclude that it is good. It's okay.
You made modification. Okay, I understand. And last question: why you study only RA and RZ parameter of roughness? I think it's not enough.
We have data another, but to be more concise, we decide to present only these two parameters.
Oh, okay.
However,
Thank
you
you
can
very
in other publications we present more parameters.
Okay, thank you very much.
Thank you, Bogdan.
Thank you for your questions.
This section is now concluded. Thank you for all speakers and participants, and we will resume tomorrow at 10 o'clock. See you tomorrow. Thank you, everybody.
See you.
Bye. Thank you.